up. And here they are. And yes, those of you students who are tuning into our broadcast here who are currently out of town, yes, I will let you do this too. So just fast forward through this section. Don't do the answers. That way you can test yourself legitimately. All right. So here's what we got. Let's do this column first here. Fixed effects. There's my answer. So synonyms for fixed effects. Model for the means. I would also take the structural part of the model, and when I talk about it informally, I usually say it's the part that everybody gets, the part that's common. So fixed means everybody gets. And then in terms of level 2 variances, those are between person random effects that represent inter-individual differences or time invariant differences, and they live in the G matrix. Any other words that you had here on that one? Between? Yep. I got between right there. All right, and then that means the level 1 part is within, intra-individual time varying residual, and those variances and covariances over time live in the R matrix. So then equations. Equations are the language in which these models are expressed, and we are not native speakers of this language. So it requires a lot of practice to get to the point where you can look at these things and read them as if they were words. So I'm trying to help us get further on in that path towards learning. So empty model for regression, this one right here. Fixed effect, just beta 0. That's the grand mean because this model has no predictors of any kind. And I put E in level 2 because in this model, E represents between person variation. Because if each person only has one observation, then E is between person. However, if you were thinking of E as residual, I would also take it down here. So this one I'll give you either cell. But in terms of its inference, it's between in this model. If we pick up a multi-level model where we have more than one observation per person that we're predicting, an empty means random intercept model would look like this. The only fixed effect in the model is right here. That's gamma 0, 0, which is the fixed intercept. And if there are no predictors, it is the grand mean of the person means, the mean of the means, as it were. The terms that represent level 2 variance, that's U0. So U0I is the idea that each person gets a random intercept, or that the model has a random intercept variance in it. In this case, it's the deviation of the person mean from the sample mean of the person means. So it's how far off each person's intercept is from the grand total intercept predicted for everyone. Level 1 then, E is the residual, which is the time-specific deviation from the person's mean. Now, show of hands, how many of you put beta somewhere? No one wants to admit it. Everyone does it. Why isn't beta in my list? It's a placeholder. It's not a thing, meaning not an estimated parameter. I don't actually need beta. I could have just written it with these two terms plus E and it would have been the same model. So beta is a convenience. It's not actually necessary. So no betas anywhere in the boxes for that same reason. They are all placeholders. So, questions so far? Sir, Charlie. Yes. If everybody is balanced, it would be the same, yes. So the mean of the means is not the same thing as just the mean if each person contributes a different number of observations. So that's the distinction. So if you estimate a model that doesn't have a random intercept variance, the fixed intercept may differ versus a model where it does because of that. And you'll see that particularly when you estimate fixed versus random slopes, whether it's the slope across all the data or whether it's the average slope of the person's slopes. Those will be different numbers in unbalanced data, yes. Other questions? All right, next column then, fixed linear time. We pick up beta 1 times time in the level 1 model, which means we pick up a new fixed effect. So now we have 2 fixed effects in the model. We still have the fixed intercept, gamma 0, 0, but now it's no longer the grand mean over time, it's the predicted mean at time 0, because that's where time is centered. Gamma 1O is the fixed time slope. It's the average rate of change in y per unit time. The other 2 boxes are the same. If the highest order on the random side, on the variance side, is a random intercept, the random intercept is unconditional over time. So it's still just the difference between the person intercepts. The fixed slope model would predict parallel lines, so variance stays the same all the way across time. Right. Questions? All right. Then the last one then, we pick up a random time slope. The first box for the fixed effects is basically the same, although I've changed the wording to reflect that question, in fact, the average of the person's slopes, as opposed to just the slope through all the data. That's a distinction that matters only in unbalanced data. E is still the deviation off of the line for each person. The main change is what happens here. Just caught another typo. U1 in that box is what it should be. When we introduce a random time slope, just like the fixed time slope became just like when we introduced the fixed time slope, the fixed intercept became conditional on time 0, the same thing happens when we introduce a random time slope. The random intercept variance then becomes conditional on time 0. So if I were to draw unparalleled lines, different linear trajectories, you would get a different random intercept variance at time 0 than you would at any other time. So the random intercept variance that U0I represents, that idea, that is conditional at time 0. U1I is the random time slope for each person. It's the deviation of each person's time slope from the mean time slope. And there's one more term that gets estimated that's not shown in this version of the equations, and that's the covariance between U0 and U1. That also gets added to the model. All right, how'd you do? We'll see. Thanks for playing. This stuff is hard, right? If this were something you could teach yourself in 10 minutes, we would all be wasting our time sitting here. That's the way I look at it. I'm happy you're being challenged. Just look at it that way. Any other questions on this before I shut it down? Okay, then if you would please pass your quizzes forward, I would like to take a look and see how they went, as well as enter your credit for participating. Thank you, thank you. You got yours? Oh, and the pencils, yes. Thank you, thank you. Thank you, thank you. And thank you, thank you. All right, got them all? Thank you. Okay. Speaking of more learning opportunities, I've pulled up homework 4. And just to be clear, I want to give every single one of you an A+ in this course, even though KU won't let me, by the way. I find that very frustrating that I can't give people A+. I want to give you all the possible points. The reason that you're doing homework is because it is not enough for you to sit there and listen to me to be able to learn this stuff. You have to interact with the material. So to that end, let me help you. Do you have questions on homework 4? So far, no. That's an honest answer.
Struggling to get the macros to run. I'm not putting the right names in. On my syntax, something is off.
Something is off. Okay. Let me pull up SAS for example 5 because I think I used the macros in there. Yes, I did. Okay, hang on. I know you can't see this. Let me make it big. So for the record, you never ever have to use the macros. You can always type numbers into Excel to find things like pseudo R-square or likelihood ratio tests. The macros are just designed to make your life a little bit easier because then you don't have to do that extra step of typing things into another program. Can you see this? Do I need to make it bigger? This is available on the website, by the way. This is for download. Example 5. What day did I put that up? It's on week 8. The Monday of week 8, SAS and Excel files. That's where I'm pulling this from. So you have a copy of this. So the way the macros work, this part up here that starts with macro and end in mend, those are the programs themselves. You don't have to do anything other than make sure that these words are in your syntax and that you have ran them. So I'm just going to go ahead and do that right here. Store them in memory. And I'll go ahead and run my data in. File save does not exist. Oh, that's because it's pointing to the wrong place. Well, here's an example in troubleshooting. I'm pointing it to the wrong directory. So let me update my own code so that it works. There, it's here today. Okay. So for instance, you are asked to do a likelihood ratio test to be able to compare the fit of alternative models. So for instance, if I have fixed linear time with a random intercept versus random linear time, that's one of the combinations you have to do. The ODS output statement here is being used to save 2 tables of output to SAS data sets. The covariance parameters table, which has all of the variance components, that's useful for doing things like pseudo R-square, and InfoCrit, which saves the information criteria table that has the -2 log likelihood as well as the number of parameters. So I created these names myself. CovParms is a SAS name. You have to say that or it won't know what you're talking about. The same with InfoCrit. Those are SAS names. And if you look it up in the user's manual, that's where you can find these things. I named them myself CovFixLin. All of my names start with whatever the table is and then enough words at the end of it so that I know what I'm talking about. So you could call this Cov1 and Cov2 or whatever you want. These names are up to you. So these are the names of the SAS data sets in which this information is going to be stored. So I saved, so I start this one with fit because it's saving the fit information. Likewise for InfoCrit here, I saved the fit information under ran linear. And then to do the comparison of the two, I call the macro, meaning I make it execute filling in the pieces of information that I want for this particular run. So it's % fit test. That says to SAS, hey, go fill in this information and run this little program up here. And what it's filling in is fit fewer, meaning what is the table of fit statistics that you save from the model with fewer parameters, and then fit more, what is the name of the table from the run you saved with more? So fit fewer and fit more stay the same each time you change which two tables it's pointing to. And if you have run both of the models, so there's that one, that's my fixed linear time model, there's my random linear time model, and then I run just that little chunk of code right there, I end up with this little table at the bottom which provides the -2 log likelihood from each model, the parameters, the AIC and BIC, and then deviance difference is what this table means right here. -2 log likelihood is referred to as deviance, and so that's where that name came from. This number right here, the difference in -2 log likelihood, is what I mean when I say report the test statistic. So it's distributed as a chi-square. So that 48 means something. Relative to 2 degrees of freedom, it is very unlikely that you would get a value this large. The null hypothesis for 2 degrees of freedom is somewhere around 6. So 48 is a lot more than 6. All right, does that help? Okay. So just to reiterate, because I did get several questions about this. Don't touch anything up here, just run it. Down here, make sure as you go through your iterations that you change the name of the tables you're saving, and then take those names that you wrote and place them into the reference to the macro right here. And then it will do the math for you. So other questions on that? Or homework 4 in general? No? Going once? Twice? Okay, sold. As I was looking at the schedule, I updated some things yesterday. I'm hopeful to have lecture 6 and these examples posted by tomorrow, and we'll start those topics next week, but that means we're a couple days behind from where I had initially planned to do certain homeworks. So I bumped all of the remaining homeworks down until Thanksgiving by a week. So you would have had another one due next week. We're not ready for it yet, so it's not due until the following week. And the same is true there. So your last one will be due the Friday before Thanksgiving break, and then we have a 2-week break before the next one should be due. So I'm hopeful that the spacing will work out so that we can keep it every other week. Although I may have to fudge a little bit based on our pace through things. All right. We did that. Any other housekeeping things before we dive back in? Okay. Then what I wanted to do with the rest of today is make sure that I've hit everything that we haven't hit yet in Lecture 5, which includes some of the more technical stuff. I'm not going to lie to you, this is where shit gets hard. But what I want you to be able to hang on to, though, is the big picture of what we're trying to do. So if you can't remember the equations or the letters, don't feel bad. That's not the point. They're just a language with which to express the ideas. Hanging on to the ideas is far more important. So what we are doing is focusing on how to describe change over time. That's the big picture. In describing how people change over time, we're concerned with 2 different aspects: average change and individual change. So average change is described by fixed effects, the part that everybody gets. Individual change is described by random effects, the idea that each person needs their own of an intercept or a time slope. Whether or not we've done a good enough job describing change over time is assessed differently if you have balanced data than unbalanced data. If you have balanced data, it's possible to do an assessment of what's known as absolute fit, which is meaning how well did my model do against the best possible model. On the mean side, the best possible model is known as saturated. That's the ANOVA model. The idea that you don't try to come up with a trajectory. You just let each mean be whatever it wants to be. If your model for change fits, so if you think change is linear, then just putting in a linear slope for average change should do as good a job as letting each occasion get a different mean. You should be able to fit not worse than saturated if your model for change is accurate. Likewise, on the variance side, we have some kind of pattern in our data of variance and covariance over time. We are trying to build a model that predicts that pattern as closely as possible, but as parsimoniously as possible. If you have balanced data, then it is possible to get the answer key. That's the unstructured, everything gets to be what it wants model. So the words saturated and unstructured, you can think of them as synonymous. I use unstructured to refer to variances, and I use saturated to refer to means, but everything gets to be what it wants is the key idea. Best as possible. So if your model for random effects, does each person need their own linear slope or quadratic slope or intercept and slope or what have you? If that's good enough, then it should be able to predict this pattern of unstructured means not worse than just letting all unstructured variances, not worse than just letting all the variances and covariances be what they want. So as good a prediction with less degrees of freedom. That's the objective. If you don't have balanced data, you don't have the answer key. So all you can do is try and head in the right direction, but you'll never actually know if you're there or not. So we did equations. Let me go through, we did this picture. So this is what, the top left here is what an empty means random intercept model would predict. The top right picture is what a fixed linear model with only a random intercept would predict. And the key thing between these two pictures is that the rates of change are the same across people, either non-existent if you don't have a significant fixed effect, or they exist but they're all the same. The bottom two pictures would be predicted by a random linear slope model in which each person gets their own slope deviation. The picture on the bottom left would occur if the fixed slope is not significantly different than 0. It stays though, because random is always specified as a deviation from fixed. So even if fixed is 0, keep it. It may not stay 0 once you add other stuff to your model. If you did have a significant fixed effect and a significant random effect around it, that would create the last picture on the bottom right here. So yes, there is some degree of change on average. People need their own version of that. And so we estimate a variance across slopes, just like we'd have a variance across intercepts. Here's 2 slides on this. What happens whenever we explain residual variance? What happens to intercept variance? Does it go up, go down, or stay the same? I'll say it more slowly. Whenever we explain residual variance, such as by adding a fixed linear effect of time, what happens to the level 2 random intercept variance? Does it go up, go down, or stay the same? It does go up. Yes. Does that mean you did something wrong? No. It goes up because math. More specifically, the number that SAS gives you on your output for how much random intercept variance you have has been corrected for how much of that random intercept variance it thinks is there by chance. How does it know what chance is? It says chance is residual variance divided by level 1 sample size. So anytime you reduce your level 1 residual variance, you reduce the chance part. That makes random intercept variance go up. And that's why these things are called pseudo R-square, because sometimes R-square can actually be negative. You can have more variance than you started with if you explain variance at level 1. So we did that. Did that. Okay, here's another quick quiz. What kind of pattern of variance and covariance over time does a random intercept model say your data has? Looking for a two-word phrase, starts with a C and an S. Compound symmetry, and in English, what does that mean? All the same. All the variances are the same, all the covariances are the same. So we can talk about that in a lot of different ways. What a random intercept does on the variance side is induce a constant correlation of all the occasions from the same person. So if data come from you, it's more related. Doesn't matter if it's time 1 or time 100. Came from you, related. Random intercept is the only way that occasions are related from the same person. So people differ from each other in one way, random intercept, and that's it. When we pick up a random time slope, we're then changing the story. Now we're saying that people differ from each other in two ways. They need their own intercept deviation and they need their own slope deviation. Those slope deviations then induce a different pattern of variance and covariance over time that's not the same. It's actually time specific in a quadratic function of variance, such that the function can interpolate between unbalanced occasions. So we'll do this picture here real quick. Fixed intercept is right here. That's the sample mean value predicted at time 0. My blue person, their U0 would be negative because their intercept is below. So they get a U0 of -4 to bring them to where the 6 would be. Fixed slope, gamma 1, 0, is 6 in this picture. My blue person is growing more than average, so their slope deviation is a +2, so that they get a slope of 8. And then E is, why are you off your line today? Even after we gave you your own slope, you're still off your line. How many occasions of data do you need per person so that E is estimable? 3. Yep. If this was 2 occasion data, each person's line would fit their 2 points perfectly. And we would not be able to quantify individual differences in change separately from residual variance. And you would have really, really crappy power to detect change, by the way. 2 is never enough. So we talked about unbalanced time. When you're fitting these kinds of fixed and random slope models, you never want to round time into convenient intervals. The only reason that you would do that is so that you could make a picture of means over time. So if I have unbalanced data, I may still try to estimate a saturated means model. To do that, I'd have to round my occasions into convenient intervals, and I would do that just for descriptive purposes, just so that I can make some kind of picture as to what mean change looks like so that I know where I'm going with the analysis. But if you were to do this in an analysis, it's going to cause problems. So let's say that you're doing a study of infant development. Your babies are supposed to come in at 3 weeks, 6 weeks, 9 weeks, and 12 weeks. And you have one baby who comes in when they are supposed to the first time, and they come in the second time, and then your parents stop returning your calls and you never hear from them again. So that baby created by the red points here, their data are complete, incomplete, but they're balanced. They came in when they were supposed to, they just don't have enough occasions. We can't differentiate that baby's individual change, but they can still contribute to the estimates of fixed change. Think of another baby who came in when they were supposed to the first time, but then they came in late for the second occasion, they came in late for the third occasion, and they came in on time for the fourth. The best fitting line through those observed data points to the best of my PowerPoint ability would look like that. That is fine. But what if you thought of this instead as just time 1, time 2, and time 3? Well, now the slope would have to look like that. So just as you would never voluntarily introduce measurement error into any variable, you never want to introduce measurement error into time by pretending it's balanced when it's not. These models don't need balanced data. One thing I will note about this little person down here, if you were to try and ask SAS to estimate what the individual slopes and intercepts are for each person, you can actually do that. They are not real estimates in the sense that they're part of the model, they're predictions based on the model, but you can do that. You can add solution on the random line, actually, and get individual U estimates for each person. If you were to try to do that for this red person, their slope is going to get pushed to look more like the mean slope. And the same is true for any person who either has really discrepant predictions, they look really different than everyone else, or somebody who has less data than everyone else. To the extent that their data are considered less reliable, their predicted intercepts and slopes are going to get pushed to look like the middle. And there's a technical term for this called shrinkage. It's the idea that the distribution gets kind of shoved towards the middle whenever you output these predictions. So the point of the story is that you never ever need or want to do that. At no point in this process do we need to know what U0 and U1 are for any particular person in the sample. The estimates that you get out of SAS when they make these predictions are not really accurate. They're subject to the shrinkage problem. The good news is that we don't ever need them. We can predict why people differ from each other in intercepts and slopes without ever needing to predict what each person's actual intercept and slope should be. A more technical way of saying that, these are factor scores. Just like you can do SEM, predicting latent variables with other things or being predicted by other things, you can do multi-level models where random effects are the same thing as latent variables. You don't ever need to know what they would be for each person. So these are the models that we know right now. The first model has neither fixed nor random effects of time included. The middle one picks up a fixed effect of time by which everybody changes the same. And the third one picks up a random effect of time that then allows people to change differently. All different kinds of linear, by the way, all still linear, but to different degrees across people. How are we doing? Yeah, some people are nodding, some people are avoiding me. I'm looking at you. Are we done with lunch? Okay, that's good. Do we need to like stand up for a minute? I'm serious. Hello? Hello. Hi. Hi, how's it going? Welcome back. Do we need to stand up? Humor me. Out of your chairs. 10 seconds, please. If anyone's wearing a Fitbit, feel free to march in place or wave your hands so that you get your steps in. My stepdaughter told me that she has to take her Fitbit off whenever she plays piano because it thinks she's walking. And I thought, oh my goodness. All right, thank you. Yes. Yes, welcome back. Can you imagine if I kept you here for like 3 hours straight? Can you even? I know every year on course evaluations, there are people who say, I really wish it could be 3 hours because that's just so much more convenient. And there's people who say, oh, thank Christ it wasn't 3 hours because I never would have made it. I put myself into the second category. I have no idea how elementary and high school teachers can teach all day long. This is exhausting. Some of you used to be teachers, right? Used to be a teacher? Did you teach all day long? I'm like exhausted after an hour and a half. My hat's off to them. All right. So questions, things that I can go over or clarify as we're moving through here. All right. So this idea of piles of variance and dependency, another word that you can add to your list as to what we're doing is we are modeling reasons for dependency with random effects. So dependency means what? Do you remember? Correlation, yes. So you can think covariance too. Covariance of occasions from the same person. Why is it there? How many sources of dependency are created by having the same person give you multiple observations? These models that we're working with right now say 2. Intercept dependency and slope dependency as a separate thing. Now right now we're talking about time slopes, but it can be any variable that varies over time. So Tiffany, where are you? She's over here. Yes, so Tiffany has data where she collects lots of things over time. Like she was talking to me about pain, right? Yeah, you don't put your subjects through this class though, right? It's a different kind of pain? Okay, good. So fear of pain and things like that. And she was like, so can I have fixed and random effects of anything, not just time? And I'm like, yes! That would be a third kind of dependency. So in her study, she's interested in how fear of pain predicts pain, right? And so 4 times a day, people fill out how afraid you are and how much you hurt. Is that the gist of it? Can I pretend that's the gist of it? Close enough, right? So rather than thinking about individual differences in the effect of time, she can think about individual differences in the effect of pain fear. To what extent do you feel worse if you think you're going to feel worse or you're afraid of it? Some people are like, it's fine, I'm tough, right? You can picture that as like a flat slope, no relationship between pain, fear, and pain. And the other people are giant babies like me when I get my blood drawn and I'm whimpering like a little girl. It makes it way worse than it actually is. So I would have a really positive slope between pain, fear, and pain. Different slopes for different folks. What's on the x-axis, though, is up to you. It can be anything that is collected repeatedly over time, including time itself. So if I had a random slope of pain, fear, that would mean people differ in the extent to which their fear of pain makes them feel crappier. That induces a third reason why the data from the same person would be correlated, and it would then predict different variances and covariances as a function of pain fear in addition to time. So more broadly, what we're trying to do is keep finding new reasons for person dependency. Those reasons are substantively interesting ways that people differ from each other, until what's left, this residual variance at level 1, really is constant variance with no correlation like it's supposed to be. So we're doing this with the method of random effects, meaning that we're taking these reasons for dependency and we're putting them in as new piles of variance. Whenever I make a new pile of variance, am I explaining variation? Yes or no? No. What am I doing? I'll take separating, partitioning, attributing. I'm making a new kind of error term, but it's still error in the sense that I don't know why it is people need their own time slopes or their own effects of pain, fear, or their own effects of anything that varies over time. What those new piles allow me to do, though, is make sure that I'm testing fixed effects related to them as accurately as possible. So that's one way to handle dependency. It makes a new pile out of it. Another way is to do fixed effects instead. And this is common in other disciplines besides psychology, econometrics, sometimes political science or any kind of cross-country cultural comparisons. Panel studies is the name by these things sometimes go by. And what folks do in this case is rather than use random effects, they use fixed effects. So for instance, if I had a longitudinal study of 100 people, then I could put in a random intercept to control for intercept differences between those 100 people, or I could put in 99 dummy codes as fixed effects. So somebody's got to be my intercept, and then I would have in basically person ID as a categorical predictor, and it'd be like person 1 versus 2, 3 versus 1, 4 versus 1, 5 versus 1, and so on. I've controlled for dependency because built into the model is every possible reason why someone's intercept could differ. Likewise, If I think that people have dependency with respect to time, people change differently, I can put in 99 more interaction terms between person ID and time. So I would have person 1's slope as the reference, and then person 2's slope versus person 1's slope, and 3's slope versus 1's slope, and 4's slope versus 1's slope, and so on. And then I would have controlled for dependency related to time. But then could I test questions like, do men change differently than women? Nope. Because person ID already covered every possible person level predictor I could put in. So you have built a prediction into the model for those differences. You haven't explained why they're there. So random effects allow you to control for dependency in a way that is then potentially informative to the extent that you can predict those random effects with variables measured at the same level. So that's why I prefer the random effects approach over the fixed effects approach, and I'd be happy to give you other readings if that's something that you guys care about. But just so you're aware that there is another game in town with respect to that. All right, so we did confidence intervals. So you get to do this, practice this on your homework. Random effects confidence intervals describe individual variation in the intercepts and slopes in a way that puts it on the scale of the original data. We did predicted matrices and stuff like that. I'll fast forward to the take-home point. By including random intercepts and slopes, we come up with some kind of prediction for the variance and covariance over time that's time-specific, hopefully matches the original data as well as unstructured. That's the goal. So by putting in individual intercepts and slopes, we end up creating each person a separate predicted V matrix that takes into account when they were measured specifically. So each person gets their own custom prediction. All right. How many of you have had any kind of SEM type class? Factor analysis and that what? Oh, some of you better raise your hands. Okay, so this next piece is for you, and if you haven't, you can ignore me. I've had students come up to me before in office hours and say, well, I want to analyze this data, but I'm not sure if I need latent growth curve modeling or multi-level modeling. I'm like, eh? That's like saying, I'm not sure if I should measure in inches or centimeters. So I want you to know that these are the same damn thing, and to be able to defend which version you go with as a choice of convenience as to how easy it will be to set up your model within each type of software. So random means everybody gets their own. Random effects are the same thing as latent variables. A latent variable in a measurement context is an unobserved trait. Things like introversion or intelligence. These are things that you think people have. You can't ever tell exactly what their level is, but you can ask them lots of questions and hopefully try to infer, based on the commonality of how they respond across questions, where they would stand on this latent trait relative to other people. It is not a coincidence that I draw my random effects as circles, because they are latent variables. So let me show you how the models that you just learned would be estimated as a latent growth curve model using structural equation modeling software such as M+. It's basically just a confirmatory factor model with two latent traits. So this is my representation of that. You're probably used to seeing pictures. But here is what it would look like if you estimated a cross-sectional E-only model, where in these pictures, which is most typically how these models are described, pictures more commonly than equations, things that are real are in boxes. So these are my 4 measured variables. So I have one construct measured at 4 occasions here, y1, 2, 3, 4. Things that are not real are in circles. So the random intercept, the idea that we have an intercept, is the red circle. Right now, it has a mean that would be estimated, and that's the gamma 0, 0, but we don't have a variance for it yet, because in the model there is no random intercept variance. Each occasion's outcome has a residual variance, and we are saying that all of those residual variances are equal across time. That's our VCR matrix. To define what the random intercept means, we would fix the factor loadings all to 1, and that creates this circle effectively as just the mean of these variables. Each of these individual variables would also have an intercept as part of the model that we shut off to 0, so that basically forces all of their intercepts up here instead. If we pick up a random intercept, we were just saying that the latent factor now has a variance instead of just a mean, and this would give you an interclass correlation. If we pick up a time slope as a fixed effect, we throw in another latent variable, and right now we say it has no variance yet, but it's going to have a mean, and that mean is going to be the fixed effect of time. The loadings, again, are set to known constants that reflect how far apart in time each of these boxes is measured. So that 0, 1, 2, 3, that would be like the time column in your data. Now this brings up an interesting point. The fact that I'm labeling these as 0, 1, 2, 3 means I'm assuming I have what kind of data? Balanced. Yeah. What if somebody came in at time 1.1 or 2.5? Shit. Now what? Well, it turns out M+ at least can handle this. I'm not sure if what other programs can do, because that's the one that I mainly use. But it has an option called T-scores, by which you can feed it variables that contain what the loading should be for each person. So basically it's an individually varying time vector then. So these would be fixed to the values in that variable rather than fixed to the same constants across the sample. And last but not least, this is what a random linear slope model would look like, where we now have picked up an estimated variance for the linear slope latent factor as well as its covariance with the intercept. In other words, the vocabulary that you know, the relationships among the random effects, their variances and covariances, they live in the G matrix in SAS. The E residual variances that are left over at level 1, their variances and covariances live in the R matrix. If you say that R has equal variance over time with no covariance, that's what this picture would look like. You could, in theory, let these error variances be different over time. I would not recommend that. I would not recommend that, because what the linear slope variance is trying to do is to predict, to capture why the variance changes over time. If you let the residual variance change over time too, that's somewhat redundant. Those two forces are going to fight against each other to try and capture that one phenomenon of variance changing. So whenever possible, I would constrain these things to be equal. If they can't be equal without hurting model fit, that's a pretty good indication that your model's not good enough yet. There's some other kind of time dependency that's making those residual variances still be unequal, such as a nonlinear trend, some kind of quadratic or extra function that should be in there. The Z matrix that controls the individual time values for each person then is conveyed by these loadings right here. So when would you estimate the same models that we've been talking about using this version of software? I can think of two specific instances. One is when you want to do any kind of mediation where your random effects themselves have to be predictors of something else. In the models that we're doing in SAS, our random effects are always outcomes. We can say why they differ, but we can't have them go predict other stuff. In these models, in this software, the same model estimated in different software, it's just as easy to draw an arrow going out, predicting something else, as it is to draw an arrow going in. Another instance in which I would go to structural equation modeling software to do this same type of model is if each of these boxes was actually supposed to be a latent variable. So let's say that I have my measure of pain. Tiffany, how many items do you have measuring pain in your study? Just one? Okay, do you have any constructs that have more than one? Which one? Pain fear has 3. So if you didn't want to just add up those 3 items into an observed variable, if you wanted to account for measurement error in doing so, and not assume that the items are parallel, you could take each of these little y boxes and turn them into latent variables, such that you'd actually be estimating your random linear model on the latent variables rather than the observed variables. That would be preferable if to the extent that you have measurement error by incorporating multiple items into the same outcome. So those are the 2 instances in which this way of doing business using this software will be more advantageous. Otherwise, a lot of times it's 6 of one, half dozen in the other. When would I stick with SAS? When you have other sources of nesting or crossing, like if you have a 3-level model or a 4-level model, or you have cross dimensions of sampling that need additional random effects, then SAS is going to be more convenient because M+ will only do, it'll only use Bayes estimation for cross models, which is in and of itself an extra layer of effort that you have to go through to make sure your model has converged and all that stuff. So. If you ever have questions about what would be more useful to you, I'm happy to sit down and talk to you during office hours or otherwise. It doesn't have to be about this class, because I feel like there's a lot of misinformation or misattribution, like people who say, well, everything should be an SEM, MLM is stupid, and everything should be an MLM, SEM is stupid. Nah, 6 of one, half dozen of the other most of the time. It really boils down to which software package will you have to fight with less to get your job done. That's what it boils down to. So I have fought and fought and fought. So let me save you some time by helping you choose these options for yourself if you're ever in that position, okay? Deal? All right. All right. We have like 5 minutes left, and I don't have the strength to do estimation. But it's in chapter 5, and hopefully you've read that. If you haven't, please read it in Craig's stuff. I do want to hit just a couple of points. Testing variances greater than 0, slide 53. So in my book, you will often see likelihood ratio test results written with in parentheses a tilde and then the degrees of freedom. And in each chapter I mention why I'm doing that, but I just want to discuss this briefly, what that's for. Turns out when you're testing random effect variances and covariances, you can't exactly use the chi-square distribution for your -2 log likelihood difference. The problem is that since variances can't be negative, it's not really a 2-degree of freedom test. It's more like 1.5. So there was a paper on this from 2006 that I stole these little graphs up here from, and I stole this graph from Wikipedia. So the problem, do you see this line right here versus that one? That's the problem. And I have tried and tried, and I just can't bring myself to care. I just can't. In practice, it boils down to whenever you're doing adding a random slope and its covariance with a random intercept, rather than using a critical value of 5.99, 5.14 is more correct. There. Now you're in the know. I just can't care. There's a lot of information here, and I just can't care about this. I'm sorry. So that's why I'm like tilde, like, yeah, I know it's supposed to be a mixture, but so long as you're over 5.14, you have the right answer. So the only time to care about this is when you're in that little narrow region of on the edge of significance, should this ever matter in your life. So when you're adding just a random intercept, that's 1 degree of freedom. The critical value for 1 degree of freedom is 3.84. It should actually be 2.7, and that's the difference between these two lines. So there, now I've taught you. My recommendation is that if you're in the clear, if your obtained test statistics for -2 log likelihood difference are way above either of these numbers, forget the tilde, forget the explanation, just write it. No one's going to care. If you use the traditional test instead, you're being a little bit conservative because you're saying that there's this region between 5.1 and 5.9 where you would have called it non-significant where it actually is significant. Meh. There. Don't output use, I already did that. Okay, there, I think we got it all. Oh, one other piece, I'll just point it out. It's in chapter 5. Emil and Remel. This is slide 51. Math, ML, Remel math, extra thing. Okay? They're different. This extra thing refers to the standard errors and the covariances for the fixed effects. So there's the technical reason why when you're doing model comparisons in Remel, the means model part has to be exactly the same. Because of this extra piece, it's actually subtracted out of the likelihood. So it doesn't keep track of how well the means model fit. That's why you can't change it and expect the Remel minus 2 log likelihood to care about those changes. So the take-home message on that, model comparisons in homework 4, if you're changing the means model, meaning you're changing your fixed effects, any model comparison using minus 2 log likelihood has to be done in ML. If you're changing the variance side, it can be done in ML or Remel. Remel is better for small samples. Ta-da! Questions? All right, so next week we get to do change. One question in the back, sir.
Related to what you said about not caring about the case where there have been cases where you looked at the bias introduced by
So the difference between ML and Remel is actually very sizable until you hit about 100. Within an estimator, using 5.1 versus 5.9, I just can't care about. That's the part. The estimator thing really does matter, though. There's a considerable literature on that. So yeah, that's the part to care about. That's why I'm making you learn how to do model comparisons the right way. Okay, then I shall see you next week.